Now we're going to start section 9.9, which is starting with looking at geometric series and building other forms of our basic geometric series. So one of the four that we had to memorize was when the power series that is f of x, when it's 1 over 1 minus x. So when you have 1 over 1 minus x, the power series is the sum from 0 to infinity of x to the n. And this was the nice basic one, right? It's geometrics. It's 1 plus x squared. If you divide any two consecutive terms, you'll get an r of x, and its first term was 1. The interval of convergence is -1 to 1. Interval of convergence. So that just means, when we say that, by the way, just means even if you had an infinite number of terms, this function, this power series, will not match the function exactly for all values of x, just for that -1 to 1 interval. Sine and cosine have all real numbers for their interval of convergence. So if you could put your infinite number of terms on, then that does mean that the power series will be exactly the same as the function itself. Okay. How do we build other geometric series? I want to make one adjustment here. I don't want this to say plus or minus r, so scratch that out, please. We'll just make it minus r, or if you want to rewrite it, a over 1 minus r. This is the form, this is like our goal. We're trying to get whatever function we're given. Take a look at the example below. So we're trying to get something like this and making sure that we can fill in the pieces, like what is a, what is r, and is this 1? So the first thing I usually do is, if this says plus r, if that says plus r, I make it minus negative r. So get negative r is usually my first step. And then my second step is, I should number that 1. And then my second step is to make 1. Make 1. What do I mean by that? In this first problem, there's already a 1 right there. But let's look further down. Right here, I could switch this around, 2 plus x or 5 minus 3x. If there's a number here, I need it to be a 1 in order to be in the form of a geometric series. Oh, and why is this the goal, by the way? Sorry. Because remember, this is what a geometric series converges to. When you have a series with a times r to the n, that series converges to the first term a over 1 minus r. So, sorry, that's why we're going that way. Anyway, so if this is like a 5, I would divide every term by 5. You're allowed to do that algebraically. And then the last thing is just to set up the power series. Once you've made sure you have a minus r and you've adjusted things to make it 1, then your power series will be from 0 to infinity, a times whatever r is to the n. A could be an expression in terms of x, and r could be an expression in terms of x. It just depends. So let's look at this first example. We want a power series for x squared over 1 minus 2x. So I can tell that I should be using this geometric process, by the way, because it is a monomial divided by a binomial, and they're telling me to do a power series centered at 0, which just means I don't have any extra thing to think about. We'll talk about that later in the notes. But anyway, the goal is to get this, remember, into like sum a over 1 minus r. And maybe it's already in that form. We have the minus r, right? It says minus 2x. So we have that r is 2x. And we already have a 1 right here. The 1 is done. That means that nothing had to get divided. So a is just the top part of the fraction, which is x squared. So f of x, which is the function x squared over 1 minus 2x, it can be the power series from 0 to infinity of x squared times 2x to the n. All right, so we could build it like that. Now, for these first 3 problems, we're not going to go into interval of convergence, but for any of these, like if they ask you that in the homework, for any of these, you could do a root test. to see what the interval of convergence is and check the endpoints. But our video will get too long if we do that for every single one. Okay, so this is our series. And if you're looking for your answer in multiple choice, they may have adjusted some things. So having x's in both parts, they might have said, well, that's the same as x squared times 2 to the n times x to the n. X squared and x to the n could be adding your exponents. You could have 2 to the n and then x to the n plus 2. Right, so that could be our power series as well. Okay. And this one, looking at this, let's see. We've got 2 to the n in a numerator here. So I'm kind of thinking this is going to diverge anywhere except for at 0. But anyway, I don't want to take the time. I don't want to lengthen the video to get into interval of convergence. So we won't worry about that yet. All right, find a power series for this function. So, all right, our function right now is 4 over, let's switch it, 2 plus x, just so it's in the correct form. And so the first thing I want to make sure I have is a minus here. It's supposed to be 1 minus r. 4 over 2 minus negative x. Whatever adjustment you make, you have to be able to simplify it and get back to the original function. So I've got the minus r taken care of. The next step is to divide by 2 in the numerator and the denominator, because I want this 2 to be a 1. So 4 divided by 2 is 2. Sometimes you get a fraction up there. Like if that were a 5, I would just write 5 over 2 up there. 2 divided by 2 is 1, minus negative x divided by 2 is negative x over 2. Okay, so now that I have it in this form, a over 1 minus r, I like to write down a is 2, r is negative x over 2. And so now I know that 4 over 2 plus x has a power series from 0 to infinity of a, which is 2, times r, negative x over 2, to the n power. And again, we could do an interval of convergence for that. I'm not going to simplify it at all, but that's my power series. All right, let's look at this one. So I have the constant in front, so that's good. So I'm going to start off with what I have. F of x is x to the 4th over 5 minus 3x. So it's already minus r, so that's done. We need to get this 5 to be a 1, so I need to divide both the top and the bottom by 5. So this becomes x to the 4th over 5. 5 divided by 5 is 1, minus 3x over 5. And then you can see the a is the x to the 4th over 5, and the r is the 3x over 5. So x to the 4th over 5 minus 3x has a power series from 0 to infinity of x to the 4th over 5 times 3x over 5 to the n. All right, let's keep going. Now this one's a bit harder because we're not centered at 0. We're centered at 1. So remember, centered at 0, let's go back to our previous examples. It means that you don't have like an x minus c. These are all just x to a power, x to a power, x to a power, etc. But centered at 1 means that we should have like an x minus 1 to the n somewhere in our power series. Okay, so how do we do that? Well, this is 1 over x, first of all. So let's look at 1 over x. Why don't we look at it as maybe 1 over 0 plus x? Because we're trying to get that a over 1 minus r trick going on, right? All right, so first of all, let's go ahead and make that. There are a lot of ways to do this, but let's go ahead and make that plus x a minus negative x. Now, I need to be centered at 1. C needs to equal 1. So in this r, in this parentheses, I need to make sure that I have a center of 1. So I don't want to write negative x minus 1, because if you factor a negative out, that wouldn't give you a center of positive 1. But if you make this 1 minus x, that is a center of 1, right? 1 minus x would equal 0. That's what we're always getting to. Now, if I just put a 1 into this equation, I have to balance it out. This is kind of like that step from complete the square. I didn't really just add a 1 though. I really just added a -1. So I need to balance it out by adding 1. So instead of having a 0 here, and we'll double check this in a minute. Instead of having a 0 there, I could say 0 plus 1 is 1 minus parentheses 1 minus x. Let's double check what we have. Did we build this correctly? Does this simplify back to the original 1 over x? 1 over 1 minus 1 plus x is 1 over x. So yes, this is good. And once you get it built like this, you can see a is 1 and r is 1 minus x. So 1 over x has the power series from 0 to infinity of 1 times 1 minus x to the n. Now that we're centered, let's start doing intervals of convergence so we match the homework a little bit more. So now that we're centered somewhere other than 0, let's just do our quick interval of convergence. This one's nice and short. Remember, this converges, I'm going to say, converges by geoseries test if absolute value of 1 minus x is less than 1, negative 1 is less than 1 minus x. Oh. So what could we do? We can add 1 or subtract 1. Subtract 1 from that. Ooh, divide by a negative, so switch everything around. Which makes sense anyway. X has to be between 2 and 0. Okay. And then we need to check those endpoints. Check the endpoints. Let's see. So if I plug in 2, I get negative 1 to the n. That diverges, right? That's just a series of 1, negative 1, 1, negative 1. And if I put in 0, I get 1 to the n. That also diverges. Those are both nth term test. That's just 1 plus 1 plus 1 plus 1. All right, so the interval of convergence is 0 to 2. I want to make an adjustment on my, excuse me, on my power series. It was easy to leave it as 1 minus x to the n, but normally when we do power series, our power series are like x minus c to the something. So it's a small adjustment to make. Let's just work on that a little bit more. If I were to factor out a negative 1 from 1 minus x, I'd have, still in brackets, all of this is still to the n, I'd have negative 1 to the x minus 1, all of that to the n. And then I can simplify that to say, well, that's the same as negative 1 to the n times x minus 1 to the n. That's a better form for our power series. I would say that interval of convergence. All right, find a power series for f of x equals natural log of x centered at 1. Now, natural log of x is not something I can just do a couple of quick steps for and get it to be in this 1 over 1 minus r or a over 1 minus r form. But there is a relationship between natural log of x and 1 over x, the power series that we just found. So f prime of x is 1 over x, right? If f of x is natural log, the derivative of that is 1 over x. So I can show you the power series for f prime of x. That was my answer to this previous problem. We just figured out the power series for 1 over x is negative 1 to the n times x minus 1 to the n in that summation. Well, how do I get natural log of x from that? Isn't it true that f of x should equal the integral of f prime of x dx? Right? That's true. Okay, so f of x is going to equal the integral of the series. We did this last section. The series from 0 to infinity of negative 1 to the n times x minus 1 to the n. Don't forget a little, I think our book kind of shows it like this, dx out there. This is an indefinite integral, so I'm going to use my regular integration rules, sure. So I'm going to add 1 to the exponent that's on the x and divide by that new exponent. So I should have the sum from 0 to infinity of, this is still a negative 1 to the n. You don't add to that exponent. This becomes x minus 1 to the n plus 1 over n plus 1. And this was an indefinite integral, so I do have a plus c right here, which is sort of like, why do we have a plus c right there? But we need to figure out what that plus c is, and normally we're given an initial condition, like way back when we started this in chapter 4, we were given some sort of initial condition. But if we're kind of crafty about this and think about the center, f of 1, which would be natural log of 1, would give me 0, right? If I plug in 1 for x, this whole big summation just becomes 0 plus c. And so what is natural log of 1? Natural log is 0. So that just tells me that c is 0. And that's going to happen a lot. We're going to have indefinite integrals. And you should show that you're checking for what is this constant of integration. But it usually turns out to be 0. Okay, so we just figured out that the natural log of x has a power series from 0 to infinity of negative 1 to the n times x minus 1 to the n plus 1 over n plus 1. Now, I don't have to do a ratio test to figure out its interval of convergence. Remember, the interval of convergence from the 1 over x power series, 0 to 2, we have the same radius of convergence. We're on the same interval. It's just that we have to check the endpoints again. So we're checking endpoints to see if, now that we've done some calculus, we took a derivative, we took an integral, now that we've done calculus, does that now include a 0 or include a 2? All right, so check into your power series right here for natural log of x. If I plug in 0, I've still got negative 1 to the n. 0 becomes negative 1 to the n plus 1 over n plus 1. Now you always need to simplify those negative 1 to a powers. If those are the same number, you need to simplify what you have. If you add their exponents together, you'd have negative 1 to the 2n plus 1 over n plus 1. Now 2n plus 1 will always give you an odd number, because whether n is even or odd, you double it, make it even, add 1, it makes it odd. So this is always really just negative 1, and you wouldn't have to show this, but this is really just negative 1 over n plus 1. And I know that that diverges. It's one of those general harmonic series, but I guess we'd probably officially be doing it by like limit comparison test or something. You could probably write general harmonic. What if we plug in 2? 2 is our other option. You'd still have negative 1 to the n. Now, if you plug 2 in here, you get 1 to the n plus 1. So I'm just going to say times 1 over n plus 1. Now, this is an alternating general harmonic series that does converge. Alternating series test. Remember, if we can make it alternate and its terms are decreasing and it's continuous on the interval, this is only discontinuous at negative 1, then alternating series test works. Okay, so here's the power series, and its interval of convergence does not include 0, but does include 2. All right. What is the error bound of the alternating series remainder when looking at the fourth order Taylor polynomial at 1.1 for a natural log of x centered at x equals 1? All right, so we're looking at the remainder, absolute value. The remainder of the fourth order polynomial that approximated 1.1. Its error bound is less than or equal to absolute value of what? All right, well, we're talking about there are no 0 terms in this series, right? So we're talking about the fifth term evaluated at 1.1. All right. So we just have to figure out what the fifth term is. So I'm going to write out some terms here. Let's see. P4 of x is equal to, according to our series, I got to get it on here. So let's see. When we put in 0 for n, we get positive 1, x minus 1 to the first over 1. When we plug in 1, we get minus x minus 1 to the second over 2 plus, when I plug in 2, I've got plus x minus 1 to the third over 3 minus x minus 1 to the fourth over 4. All right, what's the one we leave off then? We're stopping here, but what's the one we leave off? Plus x minus 1 to the fifth over 5. Alternating series says plug 1.1 into that fifth term that you left off, and that's your maximum error. All right, so it would be 1.1 minus 1 to the fifth over 5. I don't really need the absolute value because that's positive. But if that were like minus, if that alternating piece would have been minus, we would ignore that part. And then this is just, 0.1 to the fifth over 5. All right, so 0.02345 5, 2. So 0.000002 is our error bound. And remember, error bound is not actual error. It's just like the ceiling for the error, the maximum possible error. Okay, a few rules. Operations within power series. So let's say f of x is the sum of a sub n times x to the n, and g of x is the sum of b sub n times x to the n. So if we put a constant in there for x, so if I want to know, f of x, what's f of kx, then that should just be me. I know this looks kind of weird, but that's the same as just saying, all right, I'll just insert a k in for this part, a kx in for this part right here, and raise that to the n. That's the same as k to the n, x to the n. All right, so you're allowed to do that. If I know a power series for e to the x, then I know a power series for e to the 2x. That's what that's saying. What if you have an e to the z? So what if you have a power series for f of x, and now you want a power series for f of x squared? It is as simple as putting this should be the other way around, as putting the z in for the n. So again, you could just say, all right, if I want f of x squared in here, I'm going to still have whatever a sub n is. I'll put the x squared in there and raise it to the n power. It becomes x to the 2n. All right, and you're still allowed to add and subtract series together. I don't have any adjustment to make on that. All right, so find a power series centered at 0 for f of x equals 3x minus 1 over x squared minus 1. So for this one, if we're trying to use our building piece, then I could say, let's rearrange things a little bit. On the first page, we have a monomial over a binomial. This is a binomial over a binomial, but the process still works. Let's do those 6 minus 1 over, switch around, 1, oh, sorry, we can't just switch it around, but it'd be negative 1 plus x squared. Now, if I want to switch it around, factor a negative out, or instead of having 3x minus 1, what if I just multiply everything by negative 1? That would be 1 minus 3x over 1 minus x squared. All right, I've got the 1 that I need. I've got the minus r that I need. So a just gets to be this big binomial right here. A gets to be 1 minus 3x. It's allowed to be more than one term. And r is just x squared. So the power series for 3x minus 1 over x squared minus 1 is the sum from 0 to infinity of a, in parentheses, is 1 minus 3x, times r, x squared, to the n power. And that could be simplified to make it to the 2n, if you'd like. All right. And we could also look at what some of those terms are if we want to expand it out. But I want to move on so we have time to do these. All right, I think we'll see this one in the homework again or something similar to it. We're going to do something similar to what we did for natural log. Find a series for arctangent of x centered at 0. Well, arctangent of x, this is not a rational expression right now. I need to start off with something rational to be able to do this geometric series idea. But remember, the derivative of arctangent of x is 1 over 1 plus x squared, right? So g prime of x is 1 over 1 plus x squared. We're used to seeing the integral of 1 over 1 plus x squared is arctangent of x, but that's because the derivative of arctangent is this. So I'm going to kind of do the same thing I did last time. I'm going to say, well, let's build this power series. Let's get it in the right form. 1 over 1 minus negative x squared. Excuse me. Got the 1 I need. I've got the minus r. So a is 1, and r is negative x squared. All right, so the power series for g prime of x is the sum from 0 to infinity of 1 factorial 1 times negative x squared to the n. Let's clean that up a bit. Negative anything to the n can be a negative 1 to the n. And then we'll just make this. All right, so we've got this little alternating series. And it looks like it's going to be all even exponents of n. So you can expand out the terms if you want. Expanding out the terms helps you to check your work. But I'm going to leave it like this for now. Okay, so this is g prime of x. Remember before we said, well, g of x is equal to the integral of g prime of x. We know that to be true back from chapter 4. So arctangent of x is equal to the integral, indefinite integral of the series from 0 to infinity of negative 1 to the n, x to the 2n. When we take that integral, we're going to use the power rule again. Be careful on your power rule. I do this if I'm working too fast. It's not x to the 2n plus 2. Remember, you're not plugging in like an n plus 1. You're literally just adding 1 to the exponent. So it is x to the 2n plus 1 over 2n plus 1. I'm so used to plugging in an n plus 1 from our previous section that sometimes I do that if I'm going too fast. So you're just adding 1 to an exponent. Just think integration. If this is x to the 4th, my next term would be x to the 5th. All right, and then we just took an indefinite integral, so that's plus c. And remember, this is saying g of x, which is arctangent of x, equals this. Now, you always think about what's happening at the center. So when I plug in 0, the entire summation goes away. So we're saying that arctangent of 0 is equal to 0 plus c. Arctangent of 0 is 0. So there's a case again where we go through this formal process, but c was 0 anyway. So if we would have forgotten about it, we would have still had the right answer. Okay, so my power series for arctangent of x is, to write it down officially, the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Again, in interest of time, because I know this is getting long, I don't want to do the interval of convergence. Oh, well, I also don't want to do it on this part because we've got to do it on this part. Follow up. What does this series converge to when x equals 1? All right, so we're looking at our value when x equals 1. So I'm not going to look at the full interval of convergence. I'm just going to plug 1 into the series and see what happens. Negative 1 to the n. If you plug in 1, you get 1 over 2n plus 1. Okay, this is an alternating series convergence, so I know that it converges at this value. Remember, the alternating series test doesn't tell you what it converges to, but the fact that I can plug 1 in here and get a value that converges means that 1 must be on the interval of convergence. So since x equals 1 is on the interval of convergence, that means that the power series at 1 is exactly equal to the function at 1. So the series converges to arctangent of 1, which is equal to pi over 4. What series converges to pi? Well, this series at 1 converges to pi over 4. So how can I make it converge to pi? Well, if I multiply the series by 4, 4 times the series from 0 to infinity of my arctangent value, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, that should converge to pi because, I'm going to write pi. Because, again, I know that when I'm plugging in x equals 1, I get pi over 4, and then I multiply by 4, and I get pi. Write a series for g of x equals 1 over 1 minus x squared, centered at 0. All right, so this is kind of going into another relationship that we're looking at. This isn't something that we can just build. It's not like saying just plug in an x squared here. But what is the relationship between 1 over 1 minus x and 1 over 1 minus x squared? 1 over 1 minus x squared is the derivative of 1 over 1 minus x. So so the integral of 1 over 1 minus x squared is equal to 1 over 1 minus x. It's hard to think in terms of integration. So if you think about this, take the derivative of 1 over 1 minus x using that little power rule. It's the same as 1 minus x to the negative 1. Take the derivative of that, you get negative 1 over 1 minus x squared, and then chain rule times negative 1. Okay, so how does that help me? I want to start off with my 1 over 1 minus x. I want to start off with my 1 over 1 minus x power series, which is that nice basic one, right? Call that x to the n. And then if I take the derivative of that, I should have the power series for g of x. All right, so the derivative of 1 over 1 minus x should be a nice little power rule here, right? N times x to the n minus 1. And that's my power series for g of x, 1 over 1 minus x, the quantity squared. In interest of time, we won't do interval of convergence. But again, since we know the interval of convergence here is 1 to negative 1, and we've just taken the derivative of that, the endpoints might change, or they might still just be negative 1 to 1. All right, we'll stop there for today.